Hi guys, this is Madhav. Here we are with a really annoying dynamics problem. I don't really mean to be irritating about this, but when I was in university they gave me a lot of stuff that was, well, worse than this. And I never understood the point of it. I was just like, why are we doing this, you know? It's so unrealistic. I don't particularly want to burden you with my misery. However, I do want to show you this approach so that if you ever unfortunately end up in a similar position as me, you know how to deal with it. And we're basically going to use the same approach that we've been using all the time, and you'll see exactly why I was so adamant about it before. That being said, you can see the problem here. And let's just intuitively think about what's happening, okay? You have this ramp with this group of things, with the system of objects, where they're released from rest and then they're going to start to move. So when you release this mass 2 in particular, it's going to go downwards. When it goes downwards, it's going to pull on this rope, which is going to go through this pulley, and it's going to pull mass 1 upwards. And then mass 1 pulling upwards, it's going to keep going until, you know, the spring force and the friction is so high that it can't keep going anymore. So what we have is we want to find the acceleration of this group of things, everything here, including the ramp, because you'll see in a second. We want to find all this at some moment in time before everything stops. So, you know, M2 has just started moving, the spring has just started pulling. It's not quite reached the full force where everything stops again, but at some moment of time in between. So, as ever, we're going to use our tried and tested approach. In this case, we don't have to draw a figure as much because, you know, we're given a picture. However, we will draw some free body diagrams. Before that though, let's just make sure we state our assumptions so that we're all clear about what's going on. We have to assume that there's no friction between the mass M3, which is the ramp, and the ground, which means this ramp, it can also move, which is going to complicate things. We are assuming that there is friction between the ramp M3 and the box M1, and we're given the coefficients of kinetic and static friction up here, though we're not going to use both of them. We're only going to end up using one of them. Sometimes they throw out that information just to trick us. We also want to define some assumptions about the system, so let the system be the three masses, M1, M2, M3, and the spring. We don't know yet if we're going to use conservation of energy, so we also want to define that let the ground be the 0 level for gravitational potential energy. To use our kinematics equations, we're not going to use kinematics equations, but in general, let's think about which restrictions we need to place to use our equations. In this case, we're going to mainly be using Newton's law, and to do this for our various objects and not be very annoyed, we want to define that the pulley is massless and frictionless, the spring is massless, and the ropes are massless and they stay tight. You know, there's no slack in the ropes. I think those are the main assumptions we have to assume that, you know, the amount that the spring is stretched by, x, which is given up here. Assume that it's not the maximum stretch, otherwise we would have the system, you know, not moving, nothing's moving, so we wouldn't be able to calculate for an acceleration. We were already given our variables because, you know, there's a bunch of variables, and we're required to find the acceleration of each of the objects, a1, a2, a3. Now, this is really complicated, it's messy, we don't like it. We're going to use our tried and tested approach, which we use every time, which is just, if you don't like it, break it down into smaller problems that, you know, are a little bit more solvable. So we're going to do that all the time. We're going to break up this group of things into individual things. We're going to break up the motion of the individual things into x and y directions. Like, we're going to break up everything we possibly can until this is a simpler problem. So let's start drawing a picture. We specifically are trying to draw free body diagrams here. So I'm going to start with M2, which is just the mass that is hanging, because that's going to be the easiest, because it only moves in one direction. Up top you have a tension force, and then it's also being pulled by its weight. Let's assume that the upwards direction is positive. Not bad. That's not too difficult as a start. Let's move on to mass 1, which is the mass on top of the ramp. So here you have a normal force that's exerted by the ramp, which is mass 3, onto this mass, which is mass 1. You also have the tension T1 that is pulling the mass up. We have to note here, it's not always going to be the case that, you know, the tension on this block is the same as the tension on this block just because they're attached to the same pulley. So we can't always assume like this is the case. The only reason we can assume this here is because the pulley is massless, so we know it's not gonna rotate, and we're going to talk about that rotation case a little bit later. Now, we also know that, you know, this mass 1, as we talked about, it's going to move up the ramp. Well, if it's moving up the ramp, that means not only are we going to have, you know, the force of the spring in the other direction, but also we're going to have a kinetic friction, because we have motion in this direction, so friction is going to oppose the direction of motion. Finally, we have the force of gravity over here, and we're going to need to define that this angle here is theta. You know, that's just the angle of the ramp, right? Theta. And then the box is over here. And because this is horizontal and gravity is pulling down vertically, we know that this is a right angle, right? So then, if we extend, you know, this line, which is we also know here, the normal force is perpendicular to the surface of the ramp, right? So we know that this here normal force, it's perpendicular to the rope, which is parallel to the surface of the ramp. Based on that, we can continue extending this direction downwards, right? So we just extended this line for the normal force in the other direction. And also let's extend a line that is parallel to the surface of the ramp. So what we're doing is line here like so, and line here like so, where this line and this line are parallel. You can't really see my triangles, but whatever. and this line is just a continuation of this line. Hopefully that's making sense. So if this is the normal direction, the perpendicular direction to the ramp, this is parallel to the ramp, then these two have to be right angles. Also, this entire angle over here, you know, this is the parallel surface, this is the perpendicular, then these two also have to be parallel for the exact same reason. Sorry, they have to be perpendicular for the exact same reason. Because they have to be perpendicular, we know this adds up to 90 degrees. Well, I'm just going to do a zoom out here so that we get the geometry. We have over here, here's an angle theta. This is a triangle. Angles have to add up to 180 degrees. So this has to be 90 degrees minus theta, because 90 degrees minus theta plus 90 degrees, that's equal to 180 degrees. Over here we have a secondary triangle where this is also 90 degrees, and we know that these two sides, you know, these two lines, as I just talked about here, they are perpendicular. So that means this angle here and this angle here, they have to add up to 90 degrees. So let's call this angle alpha for a second. We have alpha plus 90 degrees minus theta is equal to 90 degrees. They have to add up to 90 degrees, right? Subtract 90 degrees on both sides, and we have that alpha is equal to theta. Usually people just write this on diagrams. It always confused me what's going on, which is why I'm like writing this out in full for now. In the future I might just skip steps and just write that this is theta. So just so you know, here's how I reached, you know, that conclusion. Let me quickly erase all this before we move on. Here we are. So over here we know that this is theta. Let me just pencil that in. Here we are, theta. This looks a little bit messy. However, it might help us to realize that all that's going on is you have forces in this direction, you know, perpendicular to the surface. So let that be our y-axis, because, you know, it's convenience. Here we are. And then the other forces are on they're parallel to the surface of the ramp, right? So you have friction, the spring force, and the tension on that axis, on that direction. So let this be our x-axis. That'll mean that we need to find, you know, which parts of this weight go on the x-axis and which on the y-axis. But it's better than like picking y to be up and then we have to find for all of these four vectors what part of them points in the y-axis vertically. Lastly, let's draw a free body diagram here for the ramp itself. It's going to be similar to, you know, this diagram a little bit. In particular, we know that if, you know, the ramp mass 3 is exerting a force onto 1, you know, the block, then the mass 1 also exerts a force back by Newton's third law. I think it's the third one. I never kept track of which one's which. Anyways, it's going to exert a force in the opposite direction. That doesn't look opposite. How about that? That's roughly opposite, right? You know, it goes up this way, 3 onto 1, so 1 onto 3 is this way. This is always the case with contact forces. Whenever you're drawing these free body diagrams, remember that if you have a contact force, then you need to have two of them come in pairs. One goes this way, the other goes in the other direction. You have a normal force on the ramp from the ground, right? The ramp's not sinking into the ground. You don't have any friction anywhere because there's no friction between the ramp and the ground. So you basically just have these forces plus the weight of the ramp, m3g. Okay, in this case we have more forces in the vertical direction than in the perpendicular to the ramp direction. So we're going to choose these to be the coordinates, right? X and Y. Let me draw that a little bit more straightly. Is that a word? X is directly horizontal, Y is directly vertical. If we're going to do that, then we need to decompose this vector into its components. Wow, that's fancy wording. We need to find which part of this force is in the horizontal direction and the vertical direction. So again, I could draw out this entire diagram and then we know that I'm gonna skip some steps here. We have a theta here. By the same reasoning that I specified above, we have a theta here, which means that we have this to be 90 minus theta, and this is theta. I'm sorry I rushed through that, just want to keep this tutorial short, but if you're thinking about it, just really big, draw out a big diagram that looks like this, and then work through the angles yourself. I always found that helped me. I don't like skipping steps, but just for time I'm gonna move on for now. So I think this is our picture done. We have our forces. Looks a little bit messy, but hopefully if we just consider one of these things in one of the axes at a time, then it will get simpler. So I'm gonna save this here, and I'm gonna import it into Google Docs. I think it's this one. Let's just crop out the stuff we don't need, and you see this is where our table of equations are going to be delightful for us. They're going to be a gift from the heavens, because otherwise there's no way we're going to be able to keep track of all of this mess in our heads, or just randomly scribbling equations on a page. That's not going to work. So here we are done with our pictures. Now let's move on to our table of equations. So with the table of equations, what we really want to do is we're just gonna repeat this law a billion times. That's basically what's gonna happen. So Newton's second law, we're gonna repeat it every single time for every single object, for every single axis, so you can kind of go on autopilot a bit. I'm gonna leave a lot of room for equations right here, because we're probably gonna end up with a bunch. Here we are. You'll see that this is much better than the equivalent, the alternative of just putting in a bunch of equations on a page randomly and trying to keep track of all the information in your head. Let us number these. There we are. Let's start with object 2, because it's the easiest as ever. So I'm just going to put in a reference. Hey, we're dealing with object 2. In this case, we have the positive direction to be up, so we have T1, it's positive, minus M2G. These are the forces, the net forces, yeah? So I'm going to put this equation here so you can remember what we're doing every single time. F net, the net forces, they're equal to the mass times the acceleration. So the net forces here, they're equal to the mass, m2, times the acceleration, a2. And we're done with 2. Yay, that wasn't too hard. Alright, let's move on to 1. And let's start with the x direction for 1, which is this way. Let me include the axes. There we are. It's this way. So in the positive direction we have t1 again, and we're going to subtract away the force from kinetic friction because it's in the negative direction, and the spring force also in the negative direction, and that gives us m1 a1. Before we continue to the y-axis, we don't know what Fk is, so let's just write a definition of that, just using the standard formula. Fk is Fn, the normal force, times mu k, the coefficient of static friction. Now we can move on to the y-axis here. So in this direction, oh, we forgot one thing with m1. We mustn't be so stupid. We also need the horizontal part of gravity. So this is going to be, I showed you how we calculate this in the last video, so I'm just going to not show the trigonometric diagram here for now, and I'm just going to write out what it's going to be. It's going to be m1g cos theta, sine theta, sine theta. And if you're wondering, like, how did he do that, I'd encourage you to watch the last video so that you don't feel lost. I understand I always felt lost when people did that at first, so just go back there, get comfortable with it. So that is in the x direction. Now we can move on to the y direction. So in the y direction we have the force from 3 onto 1, which is the normal force. So in this case that's the normal force, so I'm just going to replace Fn with 3 onto 1. That's in the positive direction, and then you're taking away the vertical component of m1g, or I should say the y component of m1g. So we have F3 onto 1 here. It's equal to F3 onto 1 minus the vertical component of m1g, which is going to be m1g cos theta. It's equal to m1 a1. Nope, it's not. Well, I guess it technically is, but hey, the mass, the box, it's not going to sink through the floor of the ramp, so we know that there's no movement in that direction. And so as a result, this is just 0, and so m1 times 0, it doesn't matter, it's still 0, so we can just put a 0 there. Cool. I think we're done with this, the vertical direction and the horizontal direction. So let's move on to the last mass, m3. Again, we're gonna split up the x and the y directions. Let's start with the x. Here it's simple, you only have one force that has any part along the x-axis, which is F1 onto 3, so the force of the box onto the ramp. From this trigonometry diagram again, you can see that this horizontal force is going to be F1 onto 3 sine theta. That's the only force, that's, the net force, so that is going to be m3 a3. Just before we move on, let's make sure we define what F1 onto 3 is. equal and opposite reaction, right? It's not too hard. F1 onto 3 is just negative F3 onto 1. So the force from the mass onto the ramp, it's just the same in magnitude as the force from the ramp onto the box, but opposite in direction. Finally, I think we can move on to the last one. So what is it for mass 3? What are the forces in the y direction? Again, the ramp, mass 3, it's not sinking into the ground, it's not floating into midair, it has no motion along that axis. So again, we're gonna have, in this case, the normal force from the ground, Fn, that's in the positive upwards direction, minus the weight of the ramp, m3g, minus the y component of this force right here from the mass onto the ramp. So that's going to be F1 onto 3 cos theta. All this is equal to 0, right? Now there is one last crucial step. Okay, so this part, it was basically on autopilot. We weren't really brainstorming equations, we were just reusing the same equation every single time, every single object, every single axis. Now, we do need to think a little bit about what's going on. So, if you take a look at, this setup here that we have here, when mass 2 goes down some bits, right? When it goes down some bits, the rope's going to come down with it. This rope over here is going to go forward, and then the mass is going to go forward. So if M2, it goes down by 10 centimeters, then mass 1 goes forward by, 10 centimeters. It's not going to be in the same direction, but it's the same distance, right? So let's make sure to specify that. This is for masses 1 and 2. Whatever the displacement of mass 1 is, it's going to be equal to the displacement of mass 2. I think we have the equations we need for now. If not, we can go back, and as ever, you can count the unknowns, count the variables to figure out if you need to generate more equations. But I'm going to start solving for now. The first thing that I want to do here is I want to turn this equation into an equation that relates the accelerations of both objects. So remember, acceleration is just the rate of change of displacement over time. So displacement over time is velocity, velocity over time is acceleration, so acceleration is displacement over time. So in more fancy math wording, what we have is, if we take the double derivative of this expression, you have to do the same on the left and the right. So delta S1, that's going to be equal to the double derivative of delta S2. If this just looks like weird fancy math jargon just landed on from some alien planet, just remember that we're just saying that whenever the box 2 is moving, the box 1 is moving. It's moving by the same amount, it's moving with the same velocity, it's moving with the same acceleration. That's what we're saying, and that's what we're gonna get here. If we simplify this, then we get that A1 is equal to A2, which is gonna greatly simplify our life. So ignore this if it doesn't make sense. If it does, great. Otherwise, just think, intuitively about what's going on. Now, I think we are ready to start plugging and chugging, as some teachers of mine like to say. Let's go for the easy equations. So the easy equations are going to be these ones, where you have like 0 on the right, because that just means you can add this thing to both sides, and then you're going to be left with, you know, this variable by itself. So let's isolate for f3 onto 1 in 4, and what we're going to get by doing what I just suggested, adding that second term on both sides, we're going to get, that these two things are equal. Let's call this equation 11. Let's substitute equation 11 into equation 6, because that's pretty easy too, right? We're just saying that f1 onto 3 is the negative of this stuff over here. There we go, that's not bad, right? That's not too difficult so far. What else might we want to do? One thing is we probably want to get rid of like either the a1s or the a2s so that we can solve for one and not both, right? Let's not make our lives too complicated. This thing looks more simple to me than this, so what I'm going to do is I'm going to isolate for a1 here, and then I'm going to try and plug that in somewhere over here. That's the general strategy. So let us plug equation 10 into equation 1, which is a pretty simple substitution. We're just saying replace the variable a2 with a1. So we have a2 to a1, here we are. And let's also isolate for a1 here before we carry on. So to isolate for a1, I'm just going to divide both sides by m2, right? Right. Let's affirm myself here. So dividing both sides by t, okay, divide this by m2, and then we have m2g, also this is the second term, also divided by m2. Obviously m2g divided by m2, you just cancel out the top and the bottom and you get this. Let's call this equation 13. Okay. We're gonna eventually want to substitute this over here. However, one of the issues is we still have some unknown terms here with this, you know, kinetic frictional thing. So let's just make that happen for a sec. So we know f3 onto 1 from this equation here, it's 11. So let's substitute 11. You can see what I'm doing here, right? I'm just like filling in the missing puzzle pieces. I'm just finding the variables that I don't know, using the variables that I keep on figuring out at each step. So I'm going to substitute 11 here, f3 onto 1, into 3, which gives me let me copy that over so you can see the substitution I'm making. So we know what mu k is. It was one of the given pieces of information for us. So we just have to take f3 onto 1 and substitute in, you know, this expression right here for that. Let's call this 14. Lots of equations. All right. So we want to make our substitution happen. We have an expression for a1. We have an expression for fk. We know all this. We know all this. Yeah, we're ready to make our substitution. So let's substitute 14 and 13, this expression for a1, into equation 2. So I'm going to take this here and let's just take fk, right? We're going to make the substitution here. a1, we're going to make this substitution here. Let's not forget our brackets here while we're substituting, right? This is being multiplied by something, so we don't want to forget our brackets. And this is a mess, so let's simplify. What can we simplify here? Let's first of all expand this right hand side. Let's distribute so that we don't have to deal with this messy bracket. So we're going to have m1t1 minus m1g. I'm going to rewrite this as a fraction because we're going to need it soon. So we have m1 over m2 here. Whoops. It's kind of like the coefficient in front of t1. Alright, we have distributed. Now I can see, okay, what don't I know in this equation? I don't know t1, and everything else I do know. So let's isolate for t1. So I'm gonna get t1 by itself on one side of the equation. So isolate for t1. To do that, what I have to do is I'm going to subtract t1 on both sides of the equation, first of all. So if I subtract on the left hand side, then t1 minus t1, that cancels out. If I subtract on the right hand side, I just get minus t1 here. This thing over here doesn't have any t1s in it, so I'm just going to add m1g on both sides. If I add m1g on this side, then it cancels out with minus m1g. And over here, I just add an m1g right up front. There we are. There we are. Let's factor. So over here on the right, we're going to factor so that we are left with t1 times some other term. We're doing that so that we can divide out that other term. So we have t1 times this expression to factor out. Very useful, thank you Google Docs. Okay, we have m1 over m2 minus 1. There we are, factoring. And we're going to divide both sides by this thing over here so that we can isolate for t1. So we want to divide this huge business. I'm gonna put it in the numerator with this stuff down here. Google. Sometimes Google is not my friend, as you can see. So we put all this stuff in the denominator. Do I want to clean this up? I suppose I should. So you see we have m1g over here, m1g over here, m1g over here. So I'm going to move these terms closer together and then move this term at the end. I'm just rearranging the order that they're written in. I'm not changing much. Now I'm going to factor in m1g out. So you have 1 minus this one, mu k cos theta, minus this one, sine theta, minus kx. Okay, there we are. Cool. Let this be equation 15. This is why we have a table of equations, because we end up with all of these equations. And this is not even the worst problem, as you're going to see the worst one soon. So we have t1 here. Remember, we're looking for a1, a2, and a3. Well, we had an expression for a1 right here, 13. So let's substitute 15 into 13. What we'll get is a1 is equal to a1 lowercase is equal to t1, this huge mess, divided by m2. I'm just going to tack it on right here, divided by m2. Here we are. Let's simplify this a bit. So m1 over m2 over m2 times m1 over m2. The numerator and denominator just cancel out, so we have m1, and over here we have m2. Here we are. Minus g at the end. Cool. So let this be equation 16. Of course, a1 and a2 are the same, so we can also, if we're feeling lazy, just write in a1 equals a2 equals this thing. All right, we have solved for 2 of the 3 things. Can we solve for the last thing, and then we will be done? Thank goodness. So where's an equation for a3 we can use? There it is. Oh, this one's easy. We already know what f1 1, 2, 3 is. We found it right here. So substitute 12 into, what do we have? 12 into this one. Right? This one, yeah. 5. You see, the equations are saving me, otherwise I would be lost. The numbers are saving me. Okay. So we want to do this. Let's preemptively divide by m3 on both sides so that we don't have to do that later, because we're trying to isolate for a3. We know everything except f13, so let's just substitute the value for f13 over here into our nice equation. Nice in air quotes. Okay, we have 17 equations. Cool. Let's just put in the numbers. So solve numerically. Let's just put in the numbers into decimals. One thing before that, I am going to do dimension analysis this time because I'm fairly unconfident that after all this mess I got everything right. I showed you this in, I think, the second video of the series. I'm just going to do it in my head if you don't mind. So we have, or I can't do this mess in my head. I'm going to write it out if you don't mind. Okay, let's open up desmos.com/scientific. Thank you. Google Docs, amazing software. Okay, A1, it's equal to all of this mess up top. I believe it was being divided by m1 minus m2. So let's divide it by here. And okay, dimension analysis time. So m1, we know that is going to have units of kilograms. The gravitational constant, it's going to have units of meters per second squared because it's acceleration. All of this stuff over here, this should be cos theta, sine theta. All of this, it's just going to be multiplied, right? So this is some unitless number, this is some unitless number, k is a unitless number. Yeah, it's a ratio. No, it's, let's just check what we did here. This shouldn't be k, it should be mu k. Ah, there we are. Okay, it won't let me type mu k, so like mu k, whatever. So this is a unitless number. All of this is unitless numbers, so that's good grammar right there. All of these are unitless numbers, so we don't need to worry about this for dimensional analysis. Over here, k is newtons per meter. X is the distance in meters, so newtons per meter times meters, that cancels out. We have newtons here. And kilogram meters per second squared, that's also newtons, so newtons minus newtons. I'm just going to leave the kilogram meters squared. Over here we have one mass minus another mass, you end up with a mass. You cancel out the kilograms and you end up with meters per second squared here. And this is a number in meters per second squared as well. Okay, and this gets us a final result in meters per second squared. Hey, that's what we want. A1 is an acceleration, which is equal to A2, also an acceleration. It should have units of meters per second squared, so I think we done good in informal speech. So, moving on, let's just also check A3. Does this also get units of meters per second squared? Ah, mon Dieu. Okay, pardon my French. That's literal French, by the way, not one of those pardon my French thingies. Anyways, kilograms here, that cancels out, right? Kilograms up top and on the bottom. So we just care about this stuff over here. Didn't copy over the cos theta, sine theta stuff, right? That's what we had, cos theta, sine theta. Let's just write in our thetas. Okay, sine theta, unitless, right? Don't care. Cos theta, unitless, don't care. G, gravitational constant, it's going to be in meters per second squared, and voila, we have meters per second squared as the units of our answer. So our equations seem reasonable. I can't assure you that they're correct, but they at least seem reasonable. When we're solving numerically, we'll do one last check, which is check the sign of the equations. So, oh, I shouldn't have deleted everything. Okay, A1 is equal to A2. It's going to be equal to, let's copy stuff over. So we just take m1g on top, m1 minus m2 on the bottom. m1g, m1 minus m2. And it's being multiplied by 1 minus mu k cos theta minus sine theta. That just rolls off the tip of your tongue. I can't put in mu k, whatever. Mu k cos theta minus sine theta. Yeah? Yeah. And then minus kx minus g. Minus kx minus g. G is going to be 9.81 as ever. Reminder, take care of the signs either in the equations like we did here, or do it when you're finally plugging stuff in. Don't put in negative 9.81, don't double the negative signs, you're not going to like it. Anyways, times 9.81 here. M1 I think is 25 kilograms. This I think is 30 kilograms. Mu k 0.5. Cos theta, theta is 30 degrees, and sine theta is also 30 degrees. K is 90 newtons per meter times 0.1, which is the extension we had. Let's just check that the calculator is in degrees mode. Yes, it is. And it's telling us that A1 has a negative acceleration. Does that seem reasonable? I don't think so. Let's just check. Okay, so A1, it's going to go up the axis, and it should be in the positive direction, so this does not seem reasonable. I think the most likely place of error is we switch this about. Like, I think this should be nope. I don't know where we made a mistake, but we made some mistake. Doesn't invalidate the process. We should go back and check our substitutions a bit. However, this is another sense check. And let's say you were like me, writing a final exam in university, and you get through all of this work, and then your answer, it doesn't make sense, right? It shouldn't be negative. And yes, I'm violating several sig fig rules here. If you know this, just state, I know this shouldn't be negative, but I do not have time to go back and figure out where my mistake is. that in and of itself shows that you're understanding the physics of the problem, which is the important part. We need, we're trying to learn physics here. We're not trying to have flawless mathematical solving of equations, whatever. We have that, and then let's do A3, and then we can wrap up. A3, it's negative m1 over m3 g cos theta 3 g cos theta sine theta. Okay, 30 degrees, 9.81. M1 is 25, M3 I think is 100 kilograms. What's the issue? Alright, I shall. Okay, this one seems more reasonable. So this one's in the negative direction, negative 1.061. I don't care about significant figures. I'm rebelling against all my chemistry education. Anyways, here we are. Let's make sure we put in units. Here we are. Here we are. Okay. This one seems more reasonable, right? So this one's in a negative direction. Well, let's see. So this direction is positive. Does it seem reasonable that this is in the negative direction? The only force being applied is in the positive direction, so it does not seem reasonable that it's in the negative direction. Okay, this is why we have copy-paste, guys. Here we are. So this is the general approach for how do we approach a big messy problem like this. Somewhere along the way I made a mistake. I'm not sure where it is right now. However, the key part is take this big messy thing, split it up into different objects with different directions of motion, and after you split up the splits up of the big fancy thing, and after you do so much physics that you can't speak English properly anymore, make a table of equations with each equation for a different axis and object. Solve all of these, and in the end do dimensional analysis and check the direction, check the positive and negative signs, and show that you understand the physics, even if it seems your mathematical understanding is going down the drain. That's it for today. Bye.